Okay, we're starting Unit 5 today, and in Unit 5, what you're going to be doing is expanding on your knowledge of trig functions and kind of looking at them in more of like an algebraic manner. So we're going to start with something called trig identities, and trig identities are just facts that you know to be true. Okay, so I'll give you something real simple. For example, cosecant, I know that that is the reciprocal of sine, so I could write that as 1 over sine of theta. Okay, that is a trig identity because it is something that is equal to something else but written in a different way. Secant, I know that that's the reciprocal of cosine, so I can write this as 1 over cos of theta. And then I can kind of just follow suit with cotangent. Okay, now we can write cosecant as 1 over sine. That also means we can write sine as 1 over cosecant. Okay. That's not really like a typical move to write it and describe it that way, but it is still true. So we will call it an identity because it is a fact that is, not incorrect. So we're kind of just making a list here of all the different ways that we can write our trig functions. And then we've got quotient identities down here. That just means, like, is there another way you could describe tangent? Well, yeah, I could describe tangent as the sine value over the cosine value. And if I write it this way, that means cotangent would just be the reciprocal of that, which would be cos over sine. Okay, something we talked about very, very briefly in a previous section was Pythagorean identities. There are 3 of them. These 3 things in the boxes are called Pythagorean identities. I just wanted to go over to this little triangle diagram and show you why or where those Pythagorean identities come from. And we're going to start with this one here at the top. So let's say that this triangle is drawn inside of a unit circle. And we're going to say that this point is called the point x comma y. Okay, and that is right on the circle. And since this is a unit circle, that means the radius, which would be this side, is equal to 1. We're also going to assume that this triangle forms a right angle down here. Okay, and then just for the sake of making this into something trig-like, let's call this a theta value. Okay, now I know in this triangle that the distance of this bottom leg here would be called x, and the distance of this top leg here would be called y, right? But as we know, in a unit circle, the x coordinate is equal to cosine of theta, and the y coordinate is equal to sine of theta, right? So if we think about what we could, things we could do with this right triangle, we could do the Pythagorean theorem, right? And let's just look at x and y first. Pythagorean theorem is something you can apply to a right triangle, which this one is, and it would look like x squared plus y squared equals 1 squared. If we were to rewrite the x and the y as sine and cosine instead, we would get something that looks like cosine squared plus sine squared equals 1. And that is the first trig identity, Pythagorean identity, that is listed on that previous slide. Okay, now again, all this is this is a fact that is always true. So if you take cosine of an angle and square it, and then sine of the same angle and square that, and you add them together, it will always equal 1. Okay, so it's not like you're going to be plugging theta values into this thing. It's more of like an algebra identity that we will use to help us with trig proofs that you're going to see later. So this is your first Pythagorean identity. There are 3 of them, like I said, but they're all based off of this first one. So if I know how to write my first Pythagorean identity, I can get the other 2 by doing some simple algebra. So the way that that would work is you would divide each of your terms by either sine squared or cosine squared. I'm going to start with cosine squared. And when I divide each term by cosine squared, I would get 1 plus Sine over cos is tangent, so that would be tangent squared. And 1 over cos is the same as secant, so this would be secant squared. And so what you've got is you've just got yourself a new Pythagorean identity, all based off of the first one, but still just, written in a different way, so it may help us with different situations. Okay, you could also create the third trig identity by dividing by sine squared instead of cosine squared. And let's see what that would look like. So that would be cos over sine. Now it's cotangent squared. Sine over sine would be 1. And 1 over sine would be cosecant. So again, this is just another way that you could write your Pythagorean identity. It is imperative that you know all 3 of these. Okay, it's imperative you know all 3 of these. All right, let's just get to business here. Here's what some examples are going to look like on your homework assignment. And so what you're going to be doing is, it says, use a quotient identity to simplify and rewrite. It might not specify here what kind of identity to use. So I just want you to know that basically these first 2 slides have everything you need. Okay, so all of these identities and then these 3 as well are going to help you with every one of these questions. So you're going to just kind of like treat it like a puzzle. Okay, so what you're going to do is you're going to say, which one of these could I rewrite? And there's more than one way to do this. I guess the first thing that comes to my mind is that tangent can be written as sine over cosine. Okay, we don't have a theta. We have this is actually called beta. It's just like changing a variable using x and then sometimes y. This one, this is a Greek letter, so you can just write beta instead of our normal theta value. Okay, so I'll just keep cosine the same, and I'll call tangent sine over cosine because that's what it is also equal to. And then I'm going to use algebra to help me rewrite. And so when I'm using algebra, I'm looking for things that would cancel, like the cosine on top and the cosine on bottom would cancel. And that leaves me with a simplified expression. So this would just be equal to sine of beta. Let's look at another. So over here, for example, B, I'm just going to think of, whatever I think would be easiest to rewrite. So I see secant, and I automatically think 1 over cos. I see cotangent, and I think either 1 over tangent or cos over sine. I think I'll go with that one this time. And then I'll just leave the sine x as sine x there at the end. And again, your goal is to try to get things to cancel, okay? So if you happen to put maybe you put 1 over tangent here in the middle and nothing canceled with it, then that would be a sign that you need to go back and maybe come up with a different plan. So if I write it all, in this way, my cosines cancel because there's 1 on top, 1 on bottom, and my sines cancel because there's 1 on top, 1 on bottom. So this whole thing would just end up equaling 1. Okay. Example 3, the directions say use the idea of decomposing fractions to simplify and rewrite. Okay, so decomposing fractions, that's not something we've talked about before, but it's not real complicated. It just means breaking fractions apart. Okay, so for this first one, I could break it apart and I could write it as a product of 2 things. I could say that this is equal to cosecant over 1 times 1 over sine. Does that make sense? 1 over sine because the sine's on the bottom, and cosecant over 1 because the cosecant's on the top. That is decomposing fractions, kind of turning it back into a product or a sum or a difference of things. What you would do from here is you would maybe go to your list of all those identities we wrote in the first 2 slides, and you would think of a way to rewrite cosecant. So cosecant is the reciprocal of sine, right? So cosecant can be written as 1 over sine theta. And then now that I have a common trig function down here, I could maybe do top times top, bottom times bottom. And so I would end up with 1 over sine squared theta. That answer would be fine. Or you could take it one more step and say that if it's 1 over sine squared theta, that would be the same as cosecant squared theta. So either one of these answers would be just fine. And that's basically it for that question. Let's look at one more of those decomposing fractions questions. So example B, I can decompose this fraction. It's just going to look a little different than this one back here because I've got more stuff, okay? So when you have a fraction with only one term in the denominator, what you're allowed to do is you're allowed to break it up and say that this is equal to sine over cosecant minus cosecant over cosecant. Okay, and that's just kind of using rules for fractions. Think about if you were starting from this point and wanted to go backwards. Remember, the rule is you have to have a common denominator, and if you do, you subtract the numerators. We're kind of just breaking it back into that, okay? So that would be the first step. And then again, what I could do is maybe look at each fraction independently and see if I can decompose further, kind of like what I did back here. So this sine over cosecant, I'm going to decompose that and make it sine over 1 times 1 over cosecant, because I want to simplify this. So I'm going to try to figure out a way to do that over here. And then over here, I don't need to decompose because cosecant over cosecant, meaning same thing on top, same thing on bottom, would just be 1. Okay. All right, from this point, we're going to look at ways we could rewrite this fraction. So you can do it a couple different ways. But probably the easiest way would be to look at 1 over cosecant and remember that that is equal to sine. So I end up with sine x times sine x. And when you end up with something times itself, that usually equals that thing squared. So we would call this sine squared minus 1. This answer would be perfectly fine. However, I do want to show you one quick thing all the way back here, okay? So do you see how our answer is sine squared minus 1? Sine squared minus 1. All right, look at this Pythagorean identity right here. If you were to rearrange the terms, you could rearrange this equation and make it look like sine squared. It's got theta, but we have x, but that doesn't really matter. You could make it look like sine squared minus 1. If you subtracted this 1 and put the cosine on the opposite side, you could make it look like the exact problem we are dealing with. Okay, but what would it be equal to? If I switched the 1 and the cosine, I'd subtract the 1, and I would have to also subtract the cosine. So this would mean that I kind of have a new version of this identity that I can also use as fact, as truth. So sine squared theta minus 1 is equal to negative cosine squared theta. So to apply that to what we were just looking at, that means that sine squared x minus 1 could also be written as negative cosine squared of x. So you're going to find that these problems have a lot of different paths that lead to the same result. Okay, next thing on our task list is to factor. Okay, so I'm going to actually suggest that we go over here to the right, and before we factor, let's maybe make this look different. So instead of having sine inside of my polynomial, let's maybe make sine be equal to, I don't know, a. So everywhere you see a sine, let's put an a in that spot instead. So that's going to make this 2a squared minus 3a plus 1. Okay, all we're doing right now, and this is not required, but all we're doing is we're making something that looks very complicated turn back into something that we are probably more comfortable with, something we've recognized from things we've done before. So this is just a quick little trick, okay? So if you feel like this is too confusing, let's change all the signs to a's, and let's factor the trinomial that we have, okay? So I would need 2a times a to get 2a squared. I need 1 times 1 to get positive 1, but I need to choose whether it be negative or positive. I think we need positive and then a negative like that. Nope, that's not right. We need 2 negatives. Okay, once you've figured out your signs, you're going to finish the problem by rewriting the a's as sine x. Okay, so you're basically going to change it back to sines. Okay, so that means that this answer is basically showing you how you could factor this trinomial with trig functions in it. Let's try that again with b. Let's do a substitution thing. So instead of secant, I am going to write, let's see, instead of secant, I'm going to write y. You can pick whatever letter you want. So secant squared means this would be like y squared. Okay, that is factorable. It's actually called a difference of squares because the parentheses are going to actually end up looking the same, but one will have a plus and one will have a minus. So 4 plus y, 4 minus y would be equal to 16 minus y squared. And then to finish the problem, everywhere that you see a y, you're going to change it back to secant. So it'd be 4 plus secant of x, 4 minus secant of x. Okay, let's do 2 more factoring problems before we move on. So example C, we're going to factor again. You are welcome to change it to different letters. So I guess I'll do that first, and then I'll show you how you could skip that step. By the way, this is alpha. It's like a fancy A. It's a Greek letter. I think I'm going to change this to x. So we'll make cosecant of alpha x. And then we've got a cosine. Oops. We've got a cosine that we'll maybe change to a y or something. Okay, so let's rewrite this. Instead of cosecant x, instead of cosine, we're putting y. Okay, so that's going to be x minus xy squared. And the directions, remember, were to factor. So we are going to factor. We can take an x out of each term. And we can also factor this parentheses because that's a difference of squares. So that would be 1 minus y times 1 plus y. So that's all your factoring work completed. Now you're going to change it back to what it was originally. So x was originally cosecant of alpha, and y was originally cosine of alpha. So we need to make all those changes, and you are finished. Okay. Basically, the shortcut, if you feel like this changing the variables thing is just unnecessary, the shortcut would be just to kind of factor out common terms. So you would factor out a cosecant, you'd get cosecant, parentheses 1 minus cosine squared, and you would keep factoring from there. All right, this last one is a challenge problem. The reason this is a challenge problem is because it has 3 terms, and also because we have things that aren't alike. And I can't factor something out of every term like I could on that last one. So what I would need to do is try to make these all cotangents or all cosecants. Okay, now probably the easiest way, and there's more than one way, but probably the easiest way to do this is to start with cosecant squared. Give me a moment while I go back. Because if we use trig identities, I know that cosecant squared is equal to cotangent squared plus 1. So I am allowed to make that substitution because the identity says that that is a true statement. So let's make this cosine squared plus 1. And then we'll bring down the rest of the expression like that. Okay, now this puts us in a better position because now we have everything in terms of cotangent, and we actually have 2 like terms that we can combine to condense this down a little bit. The 1 minus 3, that would end up being a negative 2. Okay, now this is actually something that we can factor. It's just not real obvious probably. So what you would want to do is you would want to maybe do that change. Let's change it and change cotangent to x, and then kind of relook at it. So this, if I change it to x, it'd be x squared minus x minus 2. See how that changed it from something complicated into something that's more familiar? So now that I have it looking more normal, I'm going to try to factor. So what times what equals -2 that adds up to -1? That would be -2 times +1, right? And that's basically your answer right here, you guys, except you're going to change it back. So you're going to, instead of x, you're going to put cotangent of beta in each of those spots.